Welcome back. This is section 5.1, Introduction to Normal and Standard Distributions. We had a discrete random variable, right? That's what the probability distributions were based upon in chapter 4, where it was a binomial thing. It was like it's either going to happen or it's not, and those things were discrete. Those things were like, okay, I'm only going to see if I'm going to roll a 2, right? And it's only going to happen a certain amount of times. I can find when it's going to happen exactly 8 out of 10 times. But what if I change that discrete random variable to a continuous random variable? Something that it doesn't necessarily happen by whole values, or a more continuous type of thing, like temperature or time or weight or anything like that. A normal distribution is a continuous probability distribution for a random variable x. The graph of a normal distribution is sometimes called, or is usually called, the normal curve. It's the bell curve. Normal curve, bell curve, synonyms. A normal distribution has the following properties. This is when we get into bell curves. The mean, median, and mode are all equivalent. The data is symmetrical. The mean, median, and mode are all equivalent. Now, is everything always normally distributed? No. Mean, medians, and modes are hardly ever exactly the same. However, as you increase the amount of pieces of data that you have, as you increase that value, a lot of sets of data tend to fit to a normal distribution. And that's really where we're going to be heading toward. If you run a sample of 30 things, but then you run a sample of 3 million things, the 3 million things is going to tend to be a little bit more normally distributed than the 30 things. The mean, medians, and modes are probably going to all be equivalent, the greater the value of your n. Second thing here, the curve is a bell shape and symmetric about the mean. Obviously, it's got to be symmetrical if the mean, median, mode are all the same. Curve is bell shaped. The total area underneath the curve is equivalent to 1. Total area underneath the curve. The integral, if you will. I was probably the only person who knows what that means. The integral of the curve is equal to 1. You guys will find that out in chapter 5.
That word cannot be real.
The normal curve approaches but never touches the x-axis. It's an asymptote. On either side, it will never touch the axis, but will get closer and closer to it as it extends farther and farther away. You can say that the limit as x approaches infinity of either side, positive or negative infinity, is going to be 0, but it will never actually reach 0. Interesting wording here for my calculus students. Between mu minus sigma and mu plus sigma, the graph curves downward. The graph curves upward to the left of mu minus sigma and to the right of mu plus sigma. So if it's concave upward and then concave downward and then concave upward, that tells me I've got 2 inflection points there, right? Mm-hmm. And those inflection points are always going to happen at mu minus sigma and mu plus sigma. What is sigma again? Sigma is what? Standard deviation, right? It's the square root of the variance, right? It's the standard deviation. So at 1 standard deviation away from the mean, away from the mean, you get inflection points. And those inflection points is when it starts to change from concave upward to concave downward, or vice versa, whether you're talking about the right side inflection point or the left side inflection point. But those values is where it starts to take a turn a little bit. For those of you who don't know what an inflection point is, it's where it starts to either slow down or speed up, right? And there's a lot of interesting connections to calculus with this. Because if you find the second derivative of the normal curve, these would be where it equals 0, right? Where would the first derivative of the normal curve equal 0? Where would the first derivative of the normal curve equal 0? Mu, right. The first derivative of the normal curve would equal 0 at mu. Why? Because that's where mu is going to go flatline, right? That's where the slope of that tangent line is going to be 0. It's the slope of the tangent line. Yeah, derivative is equivalent to slope of a tangent line. So like the derivative, and you have to always define a point. So like the derivative here is negative, right? Because the slope is negative.
Okay.
The derivative here is positive because the slope is positive.
We definitely did that before, just like some numbering.
The derivative here would be 0 because the slope is 0.
I see.
So now taking a look here, the further as I increase my amount of standard deviations away from the mean, obviously the area under the curve is going to be getting smaller and smaller and smaller, right? We're going to find that the area underneath the curve is equivalent to probability as well. So the integral of the normal curve is actually probability, interestingly enough. Which curves has the greatest mean? Which curve has the greatest mean? Take a look at the scale down below. -4 all the way up to +5. Which curve or curves has the greatest mean? You might be tempted to say this one, right? Because you're like, oh, that's pretty high up. It's got to have the greatest mean, right? Where is the mean located? Yeah, along the x-axis, the middle, right? So looking here, here, and here, all those have a mean of 0. All these three means are equivalent. Right? So what does the height of the graph actually mean? Where the data is located, right? So which, based on these three, which one of these three has the biggest standard deviation? The bottom one here, right? Because it's a little bit more spread out. This one is a little bit more condensed in. So therefore, the standard deviation of this would be a lot smaller than the standard deviation of the other two, actually. Right? So, I know I'm going to say, oh, it's going to be bell curve. It's going to be bell curve. It's going to be bell curve. Not all bell curves look exactly the same. It's all based on its standard deviation and its mean and how you scale that x-axis. Right? And that's where we're actually going to be getting into standard normal distribution. This is just normal distribution. Then we're going to talk about standard normal distribution in this section as well. All right, take a look here. The scaled test scores for New York State Grade 4 Common Core Mathematics test are normally distributed. I wanted to put this problem on here because this is actually true for our Ohio State test as well. You know how our, the geometry and algebra tests that you take? Those are called norm reference tests or normally distributed tests. So basically what's going to happen is all of the states is going to take the Algebra 1 test come April, and then they're going to get all the scores back. Then they're going to determine a mean, a standard deviation, and then what they're going to do is say, well, this percentage of students should score in the middle. And then they're going to say, okay, that's the middle. That's your passing score. So what's interesting to point out is that we don't actually know a passing score. Like our passing score that we have, they say it's like 700, but that 700 is actually like a sliding scale. Wherever you show up, there's like 20-some, 40-some questions on the test. Where does that equate to a 700? We're never told because it's all based on that year's data. Okay, it's a norm reference test where they'll say, okay, we're gonna plop a normal distribution onto everybody's scores in the state, because obviously if you take a huge sample like every Algebra 1 student in the state, it's probably going to end up being normally distributed, right? Big sample size. Okay. Like the New York State Grade 4 Common Core Math test. The normal curve shown below represents this distribution. What is the mean test score? What do you estimate the mean test score to be? Something in the middle between 380 and 330, right?
Yeah.
So I would say somewhere around right. Oh, that's an eraser. Somewhere around right there. Let's see what we got here. What are these? Are these going by 20s? Nope. Going by 10s, 40, 50, 60, 70, 80. Yeah. So if these are going by 10s, 90, 305? Yeah.
What a god.
Here's
That's
304.
so smart.
304. Okay, Carter just gave me this.
Is this like a little closer?
You know what?
So the mean score we can estimate it to be 305, right? Estimate the standard deviation of this normal distribution. Well, where do you estimate the inflection points to be? Well, looks like it's going to stop being concave downward somewhere over there and there, right? Maybe a little bit further to the right on this side. That one looks good. What do you think the standard deviation is then? 45. 45?
Yes, sir.
Think about distance away from the mean. 10, 20, 30, 45. Yeah. Looks like sigma is about 45. Yeah. What does that tell us about this thing? Well, if you score a 430, what's that tell you?
You did good.
You did good in comparison to everyone else,
Yeah.
right? And that's what we're talking about here with a normally distributed test. Like, yeah, what is a 430? Well, a 430 is good, but what is good? Is good in relation to everyone else, right? You are higher than a certain percentage of the rest of the state. Okay, so thinking this way, we've got New York state assessments. We got Ohio state assessments. I just said our mean was about 700. Well, how does 700 compare to, what did we say the mean was, 305? Well, how does 700 compare to 305? What if Pennsylvania's scale, what if the mean in Pennsylvania's scale is like a 400? You need a pass or anything?
No, I have lunch. Thank you.
You're welcome. So what if Pennsylvania's score is something different? Maybe their mean is like 500, right? So how do we compare them, right? How do we compare the scales from New York to Ohio to Pennsylvania to whatever? What we can do here is make it a standard normal distribution. We can, how the x-axis on that New York problem we had, was in like the hundreds, right? Well, what if I scaled my x-axis in a different way? What if instead of an x-axis, we call it a z-axis? Well, then we could use z-scores to define where our normal distribution is going to sit. There are infinitely many normal curves with their own means and standard deviations. The normal curve with a mean of 0 and a standard deviation of 1 is called the standard normal curve. Standard normal curve. So what a standard normal curve is saying, okay, like a score of, what did we say the standard deviation was? 45? A score of 45 above the mean. Let's say 350, right? A score of 350 on a standard normal curve would relate to z-score of 1 because it is 1 standard deviation away from the mean, right? A z-score of 2 would be 2 standard deviations away from the mean. A standard score of 3, a z-score of 3 would be 3 standard deviations away from the mean, positively, right? And I could also go negatively as well. So how do you transfer from z-score or from x value to z value? Well, you take x minus mu divided by sigma. X minus mu divided by sigma. That will get you your z-score. X minus mu divided by sigma. So wherever it falls on the normal distribution, wherever it falls on the scale that you were using, New York, Ohio, Pennsylvania, whatever, you can compare a score from New York to a score from Ohio by transferring it into z-score. And then you can say, well, if a student scored a 450 in New York and a 780 in Ohio, well, maybe the z-score from New York came out to be 1. And the z-score from Ohio came out to be 1.75. I don't know, I'm just making these numbers up. Well, then you would know that the student with the z-score of 1.75 performed better than the student with the z-score of 1. because it's a higher z-score. You can compare them a little bit easier. Okay. All right. Properties of the standard normal curve. The cumulative area is close to 0 for z-scores from negative 3.49 to positive. I think that should be a plus or minus. Oh no, it should be negative, right? Think about on the left side here. On the left side here, right? We know the z-score here would be 0. 1 standard deviation away, 2 standard, I should be a little bit further because of the inflection point, 3 standard deviations away. If you go 3.49, they're saying, okay, 3.49 is close enough to far left enough on the standard normal distribution that you can say that the area is negligible. The cumulative area is close to 0 for z-scores close to negative 3.49. You can say that the probability of that thing happening is close to 0. The cumulative area increases as z-score increases. As I go to the right, the cumulative area is going to increase. The cumulative area for z equals 0 is half of the data, right? If you plop it right in the mean, z-score of 0, then it's 0.5. That's the cumulative area. Cumulative area is close to 1 for z-scores, 3.49. So 1, 2, 3.5 out here. That's almost all of the data, right? And notice how I'm saying close to. Close to. Can we say definitively 1 and definitively 3.49? No, because again, it's not ever going to reach the x-axis. Close enough for whatever we're doing, right? Close enough that we would round it off. Basically. Okay. Let's take a look here. Use the z-score tables. Oh, it's a fun day in statistics class because you guys are going to get the z-score table. You know, it's funny. I was printing these off first semester, and I was making the keys for everything, like brand new from scratch first semester. And my wife saw me using this table, and she was like, "Oh, z-score table, memories." I know what z-score tables. Yeah, it's great. It's a great time. It's a great time. This is also located in this yellow packet that you will have for every test. Yeah. Which means it is also located in that foldout in your book. So if you ever lose this sheet, it is in that foldout in the book. Honestly, if you just Google standard normal z-scores, this will be image search it. This will be the first thing that comes up. Yeah. If you just Google z-scores and do an image search, this is probably going to come up. Okay. You know what? Let me pull up. I do have the z-score table. There we go. Do it in a smart notebook file here. Okay, find the cumulative area that corresponds to a z-score of 1.54. Okay, let's learn how to read these things. If I wanted cumulative area of 1.54, notice at the top of your z-score table, you see this diagram here? This is saying, okay, the area that you're going to find in this table is cumulative area. Cumulative area, okay? So if I go and find 1.54, do you see the positives on one side and the negatives on the other? Okay, flip to the positive side. Look along the left side. You see z, just 2 digits, right? Find 1.5. Okay, we see 1.5. I'm going to highlight 1.5 row. And then where is the 4 column? Here. So do you see 9.382 at 1.54?
Yeah.
What does that mean? That means that the area under the curve is equivalent to 9.9382. You know what else that means? That the x value with that z-score is 93.8% likely to happen. That equates to probability. these z-scores equate directly to probability. Okay? Whatever the x value is, whatever your score was, New York State test, whatever it may be, that's 93.82% likely to happen. Or you can say, if I randomly predict a student's value, they're going to be ranked 93.82% above. They're going to be above 93.82% of the other people that took that test. Okay, and then we can equate this directly to percentiles too. You guys ever look at your MAP scores that you got a while back? Everything was based on like the percentile, right? You had a raw score and then you had a percentile score. That's all this is. Okay, and it's all a normally distributed test for MAP scores as well. So 0.9382, right? 0.9382. 0.9382. What about for z is negative 0.68? Try to find negative 0.68. And then I'll move you there. Negative 0.68. Negative 0.68. So I'm on the negative side, negative 0.68, second column. 2483? 2483. 0.2483. That means if your x value came out to be a z-score of negative 0.68, that is 24.83% chance happening. Yeah, that's the probability of that value, whatever that x value was, happening. What if we want to find the area underneath the curve to the right of a certain z-score? So what if I had said, I want to find the probability of a z-score being greater than 1.28? Find 1.28 for me. This is the point of the year where I need to leave one of these on here. So 1.28.8997, right? So the z-score equaling 1.28 would be, actually, no, that's a lie. Because isn't this to the left of the curve? On the left side, the probability of less than 1.28, what did we say was 0.8997? So what do I have to do to that 0.8997 to make it greater than? The complement. Yeah, 1 minus. 1 minus 0.8997 gets me 0.1003. Does that make sense?
Yeah.
So to calculate to the right of something, you just take 1 minus of the score that you find. Okay, so let's calculate greater than negative 0.4. Yeah.
Do you have to make that an inequality because it's not less than or equal to?
It doesn't matter for these curves.
Okay.
Yeah. Greater than negative 0.4. Yeah, I see on my table 0.3446.
Yeah.
Right? So probability of z less than negative 0.4 would be 0.3446. So if I go 1 minus that, it gives me 0.6554. Make sense? Understand that it is a number greater than 50%, right? Why? Because that's a negative z-score, right? And the z-score of 0 would have a 50% chance of happening. This is right on the mean. So if I say to the right of a negative, it's going to be greater than 50. If I say to the right of a positive, it's going to be less than 50%, right? Because if it's a positive z-score, it's already on the right side of the mean. And if I went to the right of that, okay, it's going to be smaller than 50%. Okay, what if you want to go in between values? What if you want to go in between values? Well, you just think about it this way. Probability of negative 1.12. I'm just going to write it like that for right now. Negative 1.12. What is negative 1.12? 0.1314? Let's find probability of 0.6.
Click on
7257, right? 0.6 is 7257. Now understand what I'm looking at here. This is going to be this area, right? This is going to be this area. What do I want to do to those numbers? Subtract them. Subtract them. Because I basically want the area in between here and here. I should put that in red. This is what I want, right? That's what I want, which is essentially all of this, take away this, right? So I'm going to say 0.7257 minus 0.1314. So the probability that it falls in between those values is 0.5943. All that is to say, just do bigger minus smaller. Bigger probability minus. Is probability ever going to be negative? Nope. You're always going to find the difference. Just find bigger minus smaller. In the homework, it does do this one time. I'm going to change this problem real quick. Okay. So you may be thinking, well, I can't do that. I don't know, that's not on my table. Well, what's the probability of 1.1? Let's do that first. 8643, right? 0.8643. Okay, probability of 2.135. Well, where is 2.13? 0.9834, right? What's 2.14? 0.9838. So we're right in the middle. 0.9836. Just find the average. You follow me there?
Yeah.
So if it's ever a 0.5 in the middle there, it does that from time to time. Then we are going to be like, when we get further on, we're gonna just kind of like set a rule that we are always going to round to the nearest 100 for a z-score. But for our purposes right now, if it's ever presented to you with around it going to the thousandth, just go in between those x values, and at that point you can estimate. Like if it's a 0.5, you go right in the middle. If it's to the left of it, go a little bit further to the left. You know what I mean? If it was like 2.131, well, you go to 2.13 and go a little bit above. Right? Estimation. So we got 0.9836 bigger minus smaller, 0.8643. Because at that point, you're really just finding percent to the nearest 100, right? Which is probability to the nearest 10,000. And if you're really concerned about probability to the nearest 10,000, I mean, you're getting pretty precise in there, right? 0.1193. Make sense? Cool. Just 4 problems for the assignment. That's it. That's all it is.
It's never just
Just 4. All it is. Just 4.
a lot.
Hold on to those z-score tables.